In problem number 18, a child has a toy. It's tied to the end of a string and it whirls around at a constant speed in a horizontal circle of path radius r. If I were to make a sketch of that, we'd have a horizontal circle here. Here's the object at some instant. If I were to look at a top view of that, we'd have something that definitely looks like circular motion. If it were moving in the clockwise direction, the direction of its instantaneous velocity, or we could call that v tan, would be tangent to the circle and perpendicular to the direction of the centripetal acceleration. By definition, we know that the centripetal acceleration is equal to v squared over r, where v, in this case, can be described as distance over time. Since it's moving around at a constant speed in a circle, the distance is the circumference of the circle, and the time that it takes to do it, we call that 1 period, and we abbreviate that with a capital T. The circumference of the circle, from geometry, by the way, these geometric relationships are on your yellow equation sheets, would be 2 pi times r over period. So I have this new expression for velocity that I want to substitute into my centripetal acceleration equation, because that's what they're asking for. They're asking for the acceleration of the toy. So I can say, therefore, that the centripetal acceleration is 2 pi r over period, but I have to remember to square that. That's my expression for speed or velocity, and that's all over r. So once I square that, I get a complex fraction of 4 pi squared r squared over period squared over r. Since I have a complex fraction, I can consider the denominator of the complex fraction r over 1, and then multiply both sides by the reciprocal of 1 over r. And we see that one of the r's in the numerator cancels out with that r, and I get 4 pi squared r over period squared being an expression for acceleration. And that's where choice B becomes our best choice.